My name's Rob Martin. I'm a research and extension officer with FarmLink Research, based in Temora in the Riverina. As I say, welcome everybody for this webinar presented by the Soil CRC and us, and supported by the New South Wales Government as part of the Primary Industries Productivity and Abatement Program. I'd like to start by acknowledging the traditional owners of the land on which we're meeting today. For myself, that's the Wiradjuri people, and I'd like to pay my respects to the elders past, present and emerging. As I said, my name's Rob Martin with FarmLink. I've also got in support Chris Sims. If you want to give a quick wave, Chris. Chris is our comms manager and also supporting me in this webinar. And we have a couple of guest speakers who I will allude to shortly. Just to let you know, this webinar is being recorded, and the recording will be emailed out to all the registered attendees and also put on FarmLink's channels and the Soil CRC website. Now, on the right-hand side of your screen, there should be a chat box. There is both a chat box and a Q&A box. Feel free to put questions in the Q&A box. Felicity Harrop from Soil CRC will be with us. She'll also be putting a few links in the chat, but for questions directly, please feel free to put them into the chat box, and there'll be opportunity for discussion, which I'll read the questions out to Abe and Cassie late in the program. Today's webinar is the 7th of 7 webinars presented by the Soil CRC and supported by New South Wales Government as part of the Primary Industries Productivity and Abatement Program, also known as PIPAP. It's providing information to land managers and carbon farming to help make evidence-based decisions on their land. First webinar that was provided, we heard how visualising Australasian soils in the New South Wales East Bay provided spatial soil and land characteristics to assist with soil carbon planning. At the second webinar, we learned about interpretation of soil data and land capability for considering a soil carbon project, including the factors above and below ground impacting soil carbon, interpreting soil data to assess land suitability, and increasing soil carbon and identifying opportunities for additional land management practices to optimise soil carbon. Recording of these webinars can be found at the New South Wales Department of Primary Industries Research and Development website and Soil Network Knowledge website. Today, our presenters will focus on regional soils, including soil carbon levels we can expect in our region, and the factors that influence those soil carbon levels, management practices that can increase soil carbon levels. I'm going to introduce our presenters. I'm actually going to introduce our second one first, and that's Dr. Abe Gibson, a research fellow at Southern Cross University with extensive expertise in soil sciences, particularly focusing on soil chemistry, soil carbon sequestration, and climate change processes. His work emphasises improving soil health and productivity while exploring sustainability strategies and enhanced carbon capture in agricultural systems. Abe's research aims to integrate these findings into practical management techniques for farmers, making a measurable impact on both environmental sustainability and agricultural productivity. Abe will be handed to by Dr. Cassie Schefe, who will be presenting first. Cass is a soil scientist with over 25 years experience identifying and addressing soil constraints with deep technical understanding of soil carbon dynamics within farming systems. Through her business AgriSci, Cass works with farmers, industry and academia to support sustainable food production and holds an adjunct position with Charles Sturt University and has authored over 20 scientific journal papers and numerous conference proceedings. She is also accredited with both a certified professional soil scientist by Soil Science Australia and as a FertCare accredited advisor. I'm just going to share my screen, bear with me from the beginning, please. Yes, and there they are now. So yeah, without any further ado, I'd like to hand over to Cass. To you, please.
Thank you, Rob. And thank you to FarmLink and the Soil CRC for inviting us to hang out with you guys today. Looking forward to it. Just checking you can hear me okay. I've had a few issues this morning. It's good. All righty, let's kick into it and see if it's going to work. All right, so that's all good. See my screen? Perfect. All right, so this morning, as Rob mentioned, we're really getting into what soil carbon means in your region and opportunities that are available to us in order to tweak the systems and improve those if we can, and also recognising what kind of parameters or what challenges we might have in our systems that might be holding us back. So we'll have a quick work through how soil carbon is made in soils, which is something we kind of take for granted a bit. Some of the factors that affect our potential soil carbon values, how we can set up for carbon success. We'll focus a bit on what soil carbon looks like in our mixed and our cropping systems. And then I'll hand over to Abe to work through some recent trial results and some of the data coming out of the regions in this space. So first of all, as you all know, the region that FarmLink operates in is very much a bit of a box of licorice all sorts. We've got some really nice soils in there, really nice rainfall zones, all the way through to some of our medium and then into our low rainfall zones. So as any farmers who are with us would completely appreciate this, the variation in soil type and potential in those systems can vary quite broadly. We also appreciate that there's a lot of variability in our farming systems in this region, moving from continuous cropping systems. We've got a lot of just livestock operations. And then as we see in a lot of our ag is very much that mixed farming approach. The key message from this, that again, doesn't need to be a rocket scientist to work out, is that we're not looking at any one size fits all approach. If there was a silver bullet or a one hit wonder in terms of how we can solve for all our soil challenges and in particular soil carbon, I think we would have probably stumbled across it by now. But really appreciating the real strength and diversity in this region is around the variation in what farmers are doing. And it's through that variation that we can all learn kind of what we could tweak and potentially how we can improve. So just on that variation in rainfall zones, just wanted to set the scene and a bit of expectations around what opportunities there might be or where we might be targeting in our soils. So this is some work that was done by Carl Anderson and Warwick Badgery, which really showed a very strong relationship between annual rainfall down on the y-axis and then the average organic carbon levels on the y. And we can see that our 0 to 10 depth samples are really sitting at or below about 1.5% in these systems. And then if we go deeper into our 10 to 20 zone, we can see that we're really, expectations of any high levels in that are really not really going to happen. So if we can work on our 0.5 to 7 in our 10 to 20 zone and then our 0 to 10s, knowing that a lot of our dryland systems do have that little stratification of carbon because we're not incorporating or mixing those profiles very much. So just to step back about how soil carbon is made, this isn't telling you anything new, but it's really just resetting expectations around what we're working with. In a lot of our conversations around soil carbon, a lot of the media and the promotional information out there around how we can increase soil carbon levels, there's really an expectation that carbon is this static black box in our soils. We can tie a bow around it, we can put a dollar sign on it, and it's very much just a thing that exists. What we tend to forget about a bit with our soil carbon in our soils is that it all comes from, most of it, there are other sources, but most of it comes from soil organic matter. And the soil organic matter in our soils predominantly comes from the plants that we grow in it. So if we think right back to the start, if we think about photosynthesis as that key connection point from which carbon dioxide in the atmosphere moves into the plant and then gets converted into carbohydrates and plant biomass. That's the ultimate carbon sink piece. If we can't do that piece well, then everything else is already limited. So we know that once our plants die, the microbes decompose that plant litter, breaking it down into what we would consider organic matter. Those microbes then die, they're eaten by other microbes, and that starts to create these more stable fractions of organic matter in our systems. Now, if we have a net accumulation of carbon in that process, we could say that we have sequestered or captured carbon from the atmosphere. And when we talk about accumulation, we're talking about kind of increases in that more stable forms or more long-term pools of carbon in our soils. Now, the challenge with this is that most of the microbes in our soil are like us. So they breathe in oxygen and they breathe out CO2. So when we have more microbes in our system, we also have more loss of carbon dioxide back to the atmosphere. In addition, these microbes will also breathe out nitrous oxide and other greenhouse gases, subject to soil moisture conditions and kind of what populations are present. So we can really see that this isn't a perfect process. And if it was, our soil carbon levels would already be going through the roof because of the amount of residues that we're putting back into the system. So if we focus on the plant as the key mechanism in this soil carbon space, then it all becomes quite simple around how we can actually work with that carbon and work with that plant. As we know, it's not a perfect process, and we also know that every region and every soil type has different factors that drive or limit the carbon accumulation in those systems. We know that soils in our tropical and subtropical regions do have more capacity to build and hold carbon because of that moist and warm soils. So we've got high biomass inputs because everything grows so well up there, and we have high biological activity. So the cycling is going really fast with really high efficiency of conversion. We also know that soil type and condition is really important. So our sandy soils can hold less carbon because they have less ability to actually chemically bond with it. And we'll say it's less cation exchange capacity or less binding sites. We also know that our low pH soils can hold less carbon because of their impaired microbial function. As our pH drops, that's less ability of the microbes to do their jobs properly, which means we're not getting that cycling and breakdown happening. We also know that if we have crusted, dispersive or compacted soils, they're also limited in the amount of carbon they can accumulate because we've got very low or poor water infiltration and low oxygen movement through. So the key things that are required for microbes to work well. So really before focusing on anything to do with carbon, it's really important that we focus on addressing what the key limitations are that might be stopping those soils from holding and accumulating carbon as much as they can. The other thing to think about is that each soil has a threshold carbon capacity based on its environment and its climate, soil type and management. It's not a linear increase, as we all know in reality, and so managing expectations around what's possible is really important. The other thing is we think that, if we just increase our organic inputs all the time, we keep all our residues in the system, we add composts and manures and everything else that we can, if our soils are starting from a low carbon base, there will be some increase, but we're talking about diminishing returns. The other thing we know is when we add organic materials like compost to the system, they actually spark up the microbial community, increasing the loss of carbon as CO2, which then actually causes that to burn off and deplete over time. So the more we're looking to hit those higher levels of carbon, the more we're talking about diminishing returns and additional cost per unit. So in terms of setting up for carbon success, the really key thing that we've already flagged is to manage those constraints. So if we think about good old Liebig and his wine barrel, wherever the lowest hole is, whatever the most limiting factor is to plant growth, that's the key thing that will also stop our soil carbon from accumulating as much as it can. And in our systems around in the FarmLink region, we know that soil pH and acidity is generally the most limiting factor in terms of productive farming systems. We know that's a factor because we're getting really good at farming. The management and systems in the FarmLink region are really well optimised, which means that we're actually exporting a lot of product, we're moving a lot of material off paddock, which means that we're by default acidifying our systems, as everything that we move off is really high in alkali. So all our agriculture is net acidifying, and in the FarmLink area, which does have some really nice, highly productive systems, that rate of acidity continues to increase. So that's something that we cannot forget at all. Any soil type, any system, anything that's not functioning as well as you think it can, really important to get some soil pH tests done to understand what's going on. The thing about acidity is it limits everything in the system. So there's many plant species that can't grow well and persist at low pH levels. Many of our nutrients are less available. So phosphorus, nitrogen, potassium, sulfur, calcium, manganese, molybdenum, there's a really key part there. And the nitrogen story is really important, knowing that a lot of our fertilisers that we apply in acid soils aren't going to be well used. We also have really poor plant response to our fertilisers that we apply, both our N and particularly our P. As I've already mentioned, we have reduced microbial function. And a key part of that is the nitrogen cycling legumes. So in our system and the microbia, the microbes that are responsible for that cycling. So an example is with some clover. So clover in the picture here is those plants that are grown in good pH conditions are well nodulated, good vigorous plants. In low pH conditions, poor nodulation and poor growth. Poor persistence of lucerne stands is also a key indicator that there might be an acidity issue. And we're getting poor nitrogen mineralisation from organic matter. So we're not getting the breakdown and release of mineral N that we'd expect. The next thing is, once we've adjusted our pH through an appropriate liming strategy, it's really important then to say, well, what's next on the leaky barrel? Ensure that there aren't other soil conditions that are limiting plant growth. So what's the next one off the list that we can continue to work through? In terms of other constraints in the region, there's a bit of everything going on. So we know that there's a bit of sodicity, both surface and subsurface in FarmLink regions, and this has an impact on soil structure, infiltration and plant establishment. There are some pockets of salinity, which can decrease the ability of the plant to take up water. Depending on your farming system, historical compaction may also be an issue, particularly where there's, particularly in the last few years, where you may have had to be running heavy machinery at harvest over soils that may have quite a bit of moisture in them. So we may be getting some of that compaction going on. Waterlogging and drainage issues is an ongoing challenge in our wetter years of the cycles, and this also reduces the oxygen availability to roots and microbes. It also shuts down microbial functions such as nitrification. So in our waterlogged soils, we're not moving that nitrogen from that ammonium phase through to the nitrate. And lastly, nutritional deficiencies and toxicities will reduce our plant vigour and competitiveness. So the common theme in all of this is to set up your system for optimised plant growth and microbial function. If the plant wins, then the microbes win, and then we all win. In terms of what we can do to focus on carbon in our mixed or our cropping systems, again, these are all pretty straightforward, things that we're all aware of. In terms of our management practices, the key thing is the quality of our biomass input. So we know that legume-based pastures and pulses are the best that there is in terms of increasing and improving our soil organic matter and carbon status. It's the addition of that nitrogen-rich organic matter that helps improve the efficiency of microbial decomposition and cycling, which then increases the efficiency of that organic matter accumulation and carbon increases. Part of this as well is our crop residues and maintaining those in the system as much as we can, and just general ground cover management with our mixed systems. You know, we know that any time that we've got ground cover in the system, that's enabling those microbes to work better. The other management issue is, as I've mentioned already, is around our soil constraint amelioration, so we can grow the best plant possible. And then our soil fertility aspect around that we can't maintain or grow soil carbon if we don't have adequate nutrients in the system. And we'll talk about that next. And just to put some reality check on this, over the last few years through the Cool Soil Initiative, we've sampled over 1,600 soil samples from northeast Victoria through to the southern half of New South Wales. And this has demonstrated that most of our soils with high soil carbon status are also the soils with a good pH status, and are also the ones with a legume history and good yields. So growing a good plant, growing productive plants, has really strong feedback into our soil carbon levels. And in terms of the soil carbon values that we've measured in the FarmLink region itself, but everything from 0.5 on really sandy soils all the way up to 4.9. 4.9, I reckon, is a bit of an outlier, but we consistently see measurements up to 3.5. So that is possible within our climatic conditions. So in terms of fertility, as I mentioned, we can't grow carbon in our soils unless we have the right nutrients to go with them. So if you think about organic matter in our soils, we tend to think of it just as being carbon, but actually that organic matter is composed of carbon and other nutrients as well, such as phosphorus, potassium, nitrogen, sulfur, oxygen. You know, it's all in the mix. And some really important work done in the early 2000s by Clive Kirkby and crew worked out that there was very strong, clear ratios between the presence of carbon in our soils and other nutrients in that organic matter. So if we look at the graphs down the bottom here, we can see that if we measure our total soil carbon in our organic matter on the y-axis, and then our different nutrients, nitrogen, organic P, which is more of a inherent fertility rather than inorganic P, and then soil sulfur, we can see very clear relationships between them. As our fertility improves, so our ability to hold carbon improves. So we can't improve carbon on fertility or on nutrient deficient soils. And for some of our soils, it may be that something like phosphorus might be the key limiter in our systems that then will enable us to take a step change for our carbon levels. On the left here is another more detailed approach in terms of looking at the impact of nitrogen fertility on soil carbon. So if we look at this is a time series work from 1985 to 2010, and we have different soil organic carbon levels on the y-axis. And we can see that as we go from N0, so that's 0 nitrogen, all the way to 180 kilos of N per hectare, you can see that over time, increasing nitrogen status in these previously highly depleted soils has had an impact on our carbon status. This has also come through in work in Victoria, New South Wales through historic fertiliser trials. Previous replicated trials by Institute Pivot and other FERT companies have shown that where we have high N and P status soils, they also have an increase in our soil carbon levels. So the last thing I wanted to touch on before handing over to Abe was just the concept of the importance of maintaining soil carbon levels. And this is something that I tend to speak about a bit. So for those who may have heard me mention this before, is that we always focus on increasing soil carbon and what can we do to increase it. As we've spoken this morning, I hope you appreciate that soil carbon in our system through organic matter is highly cycling. We also know that in our farming systems, we're exporting so much. We're exporting nutrients all the time. We're exporting carbon through our produce as well. But just to think about another way of looking at this, if we consider that stable organic matter has a carbon to nitrogen of about 10 to 1, it's not quite there, but it's easy to do the maths this way. And if we went out and did a soil sample and our soil carbon value came back at 1%, in around FarmLink area, we'd be hoping for at least 1.5, but let's just say 1 to keep it the maths easy. Then through that season, if we've mineralised 100 kilos of nitrogen for plant uptake, which we build into our calculators. So we're working at least 50 kilos of mineralised N, through the season, which we adjust our nitrogen vert budgets around. And over the summer period, if we get moisture, we could get another 50. So let's just say that we lose 100 kilos of mineral N per year out of that organic matter for plant growth. Because we're dealing with microbes in the system, and that conversion is a microbially mediated conversion, we're actually also losing carbon through that process through carbon dioxide loss. So that 10 to 1 ratio is if we're pulling out 100 kilos of nitrogen, we're also pulling out a tonne of carbon as CO2. If we're not replacing that into the system, we're going to end up with a continual drawdown of our organic matter and our organic carbon levels, which we've seen through our traditional conventional ag practices in the past. Okay, so let's say we measured soil carbon 1%, we've poured out all this mineral N and we've lost all this carbon. We then come back next year and measure the same place in paddock for soil carbon levels. If those soil carbon levels are still the same as what they were last year, so let's say 1%, that actually tells us that in addition to everything that we've done to grow a good plant and everything else, that we've pulled in 100 kilos of N and a tonne of carbon back into that organic matter. So by default, in a farming system where we're creating food and exporting food, if we're maintaining our soil carbon values over time in that incredibly fluxing system, that's actually a definition of sustainable food production. So we're not just putting in what we need in terms of our food, we're putting in what we need for our organic matter and carbon as well. So the last message I'd like to leave with you is to say that if you're maintaining our soil carbon values in a highly productive food and fibre production system, that by default actually requires ongoing carbon and nitrogen inputs because it is a constantly fluxing system. So just to maintain soil carbon levels in a food production system is amazing. If you are able to increase soil carbon levels, that's kind of gold star status, knowing that the additional inputs that are required, not just to lift those carbon levels, but also to maintain them. At that, once you reach a higher peak, you then need to continue to maintain into that higher bracket. So it all takes energy, it all takes cost, and it all takes inputs. But just recognising what you're doing really well in your systems to start with. So I'd like to leave it there and hand over to Abe.
Cass, just before you hand over, there's just a couple of questions in both the chat and the Q&A. I was just wondering if you'd be able to just have a look at those ones.
Sure.
Fantastic.
If you'd like me to read them out.
No, I can see John Grant's.
Yes, yeah, there's one in the chat and one in the Q&A.
All right, well, I've got the chat one. So where does the balance of CO2 produced by lime use and increased soil carbon sequestration due to better plant growth lie? Okay, so that's talking about the CO2 lost once the lime reacts with the soil versus the increased carbon ability for plant growth and carbon capture. So we know that when we add lime, there is at that point in time when the lime reacts with acid in the soil, that calcium carbonate then reacts to form the carbonate reacts with acidity, and then we get the production of CO2 and water. Now, we know that that is a direct CO2 loss to the atmosphere. But we also know that once we've changed that acidity, then the whole system lifts. So if we actually do the mass balance, say that the lime lost, so the CO2 lost through that actual lime application is a lot less than what we actually gain from that in terms of both increased plant growth, but also increased microbial function. And that means also if we're growing pulses or legumes in the system, we're actually getting good effective nodulation. We're getting really good use of that nitrogen, which means that we have less requirement for NFIR, which then means we have less emissions due to the use of that nitrogen fertiliser in the system. So I hope that makes sense. But if you think about lime as like an initial capital spend, and then that kind of unlocks all this additional benefit, which then increases the capacity of that soil to hold carbon. So it's definitely a positive balance. And let's have a look at the Q&A. It's not coming up for me. Oh, here it is.
Would you like me to read it to you? Yes. So the question from Warren McCauley is, how can we balance farm goals, i.e. yield, with maximum soil carbon addition? For example, since maximum carbon additions would involve not harvesting the crop and letting the entire biomass return to the soil, how can we balance these goals? Should we be fertilising for maximum yield, or is there another metric we should look at?
This is obviously a bit of a drawn out response because depending on what farming system we're working with. But I'd like to come back to this one later, but really to say that if you're optimizing your farming system to grow the best plant to then create the best yields, by default, that's also the best approach we can take for carbon. Now, if we know that if we ran a manure crop, so either green or brown, probably more so a brown manure crop where we just kill everything and let it sit on the surface, I think will have longer term benefit more so than the green, which we incorporate in. I mean, that's the perfect idea, right? If we just grow something and then we just let it die in situ. And where possible, if we can creatively work that into our farming systems, then we will get benefit from that. But if we actually need to make money by cropping, then growing the best crop plant we can, because it's the root matter as well, which is also a big source of carbon that we tend to forget. So if we can maximise the ability of those roots to explore through the soil, then that will have a big impact on our carbon. In terms of our fertilising for max yield, I think it's around maintaining background fertility. So it's rather than going hardcore with everything, if that maximum yield is also max profit, that's great. But it's around ensuring that there's good background fertility, that we do have some N in the system, preferably with some use of legumes, but even making sure that our P levels aren't subclinical. And that's something that we know in the FarmLink region. There is a lot of soils that are running borderline with P nutrition. That really should be lifted up a bit to ensure that in our no-till systems that there is enough P available for the plant. So just, working on setting up what you can, if that's excellent. That one.
Thanks, Cass. We might return to it if you have another thought on it after Abe's done.
Happy to have more of a chat about this
Absolutely.
stuff after we're done.
Cool. So please feel free to put your questions in the Q&A and or the chat. Either works. We'll be monitoring both. In the meantime, I'm going to hand over to Abe, and we'll plow on.
So hopefully everyone can see that and hear me. So thanks, Cassie, and thanks, Rob. As mentioned at the start, my name is Dave Gibson from Southern Cross Uni. And what I'll be talking about today, to sort of piggyback on the back of what Cassie was talking about, is some results from some field trials that we have been running as part of the Soil CRC, and there's sort of 4 different sites that I'm drawing on data from across Australia. And these are all the people that have helped us collect this data over the last 5, nearly 6 years now. So a big thanks to all of them, especially my colleagues at Southern Cross Uni. So these trials, what we've been looking at is the impact of plant diversity in cropping systems, and that's been impact on yields, water balance, and also nitrogen balance in these systems, but also how that impacts our what we refer to as soil health, or the sort of soil fertility, and then also soil carbon levels. And what we've been looking at for building plant diversity in cropping systems, so trying to move away from monoculture systems as the use of summer cover crops, temporary intercropping, and then what we call synchronous intercropping, which is taking two crops planted at the same time, both to harvest. So summer cover crops, they've gained a lot of traction in the Northern Hemisphere, and it's around keeping living roots in the ground in our southern systems here in Australia, keeping living roots in the ground over that summer fallow. So they're seen as important for erosion control, but the counter argument made to the use of summer cover crops is the use of water. So declining water available at sowing and how that impacts us throughout the year in terms of yield, but then also the tie-up of mineral nitrogen in more organic forms. And there's been a lot of work looking at the control of summer weeds and how that does impact the water balance and the type of nitrogen, and also contribution of summer fallow rainfall to yields. But the counter argument to that, in terms of the use of cover crops rather than weeds, or managing weeds and fallow, and why they're different to weeds, is this concept of functional diversity. So having those living roots in the ground as compared to stubble means that you're having root exudates, and then sort of those organic compounds are being provided to microbes. And I'll talk more about that as I sort of move through, and why that's an important concept for building carbon in cropping systems. So intercropping, as I mentioned before, so we have our synchronous intercropping, so taking both crops to harvest. So we have canola and fava bean here in that photo. And so we have this concept of over yielding, where you're getting higher biomass production, higher yields relative to the monoculture of the two crops. But there's also this concept of temporary intercropping that we've been looking at, where we've been looking at wheat and a legume, and you spray out that legume before you have competition for resources, which is a really important concept for Australian systems, we believe, because it can help overcome things like competition for water and increased risk of terminal drought. So our diverse cropping systems are important because they increase biomass in the system. So sort of leveraging what Cassie was talking about before. But on top of that, they also provide diversity in the compounds that are released by roots, so our root exudates, and then potentially more root exudates as well. And so when we have that occurring in our system, it promotes that microbial growth that Cassie was talking about. And then you also have concepts like increased resource use efficiency, especially in our intercropping systems, which I won't talk about too much, but I'll be happy to answer other questions about that. And so it's putting us on that pathway to a system that is producing more biomass, using resources more effectively, and therefore producing higher yields. And Cassie sort of talked about the relationship between inputs to the system through plants, and then the release of litter, and then also exudates, and then our microbial community that's really important for building our soil carbon. And when scientists sort of like me talk about soil carbon, this is the diagram that often gets put up, and it's kind of fundamentally different to our Australian cropping systems, because we have something that looks like this. So this is a drone shot from our trial site at Central West Farming Systems. We have this summer fallow, so you can see we have pretty good stubble retention there, and you can see those yellow plots where our summer cover crop has been sprayed out. Now, what I'm going to talk about is what the implications are for this and our pattern of biomass production in cropping systems, and why it sort of doesn't fit with this concept of soil carbon sequestration that we talk about so readily in grazing and higher biomass systems. Now, soil carbon, Cassie sort of talked about why it's so important. It's a really good indicator of soil health, and it's because of that, it's an indicator of the biomass that's being produced in the system. What we're also interested in are the implications for nutrient cycling and water holding capacity that we're sort of learning more and more about as we research more about soil carbon. And then also what we sort of haven't talked about too much here, but the market opportunities that soil carbon sequestration does present. Now, to sort of step through what we've seen around soil carbon building in our plant diversity trials, I'll be drawing upon data from 4 sites. So we have trial at Gunning Gap with Central West Farming Systems and Riverina Plains at Abatement. So similar soil conditions to FarmLink. We don't have a dedicated trial in the FarmLink region, but we are nearby with these plant diversity trials. We also have data from Birchip Cropping Group, which is a little bit different in terms of soil type and climate. And then also with Facey Group over in WA. While these two are really different, there is a sort of universal story around soil nutrient balance that sort of reinforces what Cassie was talking about before. The Gunning Gap and Abatement trials are long-term ones, while I've got single season data for Birchip and Facey Group that I want to leverage just because it really ties together the story. In terms of the treatments that we've been looking at for our plant diversity, so our summer cover crops, we've looked at single species and 4 species mixes at Riverina Plains, and then we've transitioned to a 3 and 9 species mix. A temporary intercrop, so our wheat and legume, and then last year we looked at synchronous intercropping with canola, Philippine potato bean. And then at Central West, again, single and 4 species, transition to that 3 and 9 species, temporary intercropping again, and now synchronous intercropping. Now, the single species and the 3 species mix are referred to as low diversity, and the 4 species and 9 species are our multi-species treatments when I start putting up the graphs. These are the climate and soil conditions. So you can see there's a little bit of variation. We sort of capture conditions across the FarmLink region and sort of the variation in soil types as well across these 4 trials. So the results that we sort of will be showing, they are relevant to the region, and that they also, as I said before, some of the stories and themes that come out that Cassie has talked about, they're going to be universal across soil types and across climate regions. Now, the key finding in relation to carbon, so at Central West, is we haven't had a treatment response since the trials have gone in 2019. So this is our time series of carbon, and you can see our different treatments there. There's some temporal variation, but in terms of a treatment difference, we haven't had one. And this is in the top 10 centimetres with multiple soil cores collected per treatment. If we break this down and start looking at the different pools of carbon at Riverina Plains, so rather than showing you basically the same graph again for River Plains, I broke it down to some indicators for some of the faster cycling pools of carbon. So water soluble carbon, hot water extractable carbon. They represent those fresher inputs, our microbial biomass, which is also representing our microbial biomass carbon measurement down here. And again, it's a similar story. We have temporal fluctuations in the labile carbon, but we don't have a treatment effect. So we're not seeing that, even though we are building this diversity that we hypothesized would build our carbon, we aren't seeing an effect because of that. Now, if we look at why this might be the case, particularly with the summer cover crop, we found that summer cover crop biomass is really hard to generate. What we've also found, summer cover crops are hard to establish in this southeastern region with our summer climate. So our summer climate, we're extremely water limited. FarmLink and Central West, you're on the borderline of summer dominant rainfall technically, but your evapotranspiration rates are just so much higher. And while you do get storms, people will see runoff in their paddocks during their fallow. It's that evaporative demand, the sporadic rainfall, the large gaps between rainfall that make it so hard to establish our summer cover crop biomass. In 2022 at River Plains, we did see a response in hydraulic conductivity, so infiltration rates. to this higher biomass cover crop, but we haven't seen any changes in our carbon, and it's that low additional biomass contribution. At Central West in that 2021 year, they did have a weed issue, struggled to control for weeds in the summer fallow. It wasn't a clean fallow. Summer weed biomass was 0.4 to 1 tonne. So if you're comparing this biomass to a system where weeds aren't as well controlled, what you get is you kind of see our summer cover crop biomass is kind of similar to our weed biomass. So we're not having that additional biomass to build that carbon. When we compare this to our, I guess our winter treatments, so our temporary intercropping, I don't have the biomass for our synchronous intercropping in here as well. But what we've found is that we're sort of not having that additional biomass. Last year in our synchronous intercropping, we did have, so for those that are familiar with the land equivalent ratios, our land equivalent ratios for flowering biomass in our synchronous intercropping treatments were sort of 1.3 to 1.4. So it was a significant increase in biomass relative to the monoculture controls. But again, it's that similar story of our cash crop production is where our major biomass is. So our cover crop and our temporary intercrop in terms of legume biomass is not having a massive effect. To sort of just deviate away from the carbon story for a second, and this is really important because if we're going to put our plant diversity treatments in, we need to understand what it's doing to our water dynamics. So each year, we have published some of the data for roof planes, and we sort of said, well, we didn't find a treatment effect in individual years. And you can sort of see that in the scatter plot here. This treatment to control water ratio is the ratio of water that's in our summer cover crop treatments divided by the water that's available in the control. And you can see that as we produce higher biomass, we have a declining trend. So a value less than 1 of water available in our summer cover crop treatments. So you can see the colours match up specific years. And so you can sort of see why we're not getting significant effects when comparing total water between treatments. But it's this declining trend across the data overall that we're sort of seeing that is problematic is probably not the right word, but we are seeing that expected effect that our summer cover crop does decline water available at sowing. But if we compare that to yield, we don't have that same negative decline. We didn't get a summer cover crop and yield in all years, so the data set is slightly different. But you can see that the grouping of our yield ratio, so treatment to control yield, on the y-axis there, our water content at sowing, that tight sort of vertical distribution shows that in-season conditions are having a pretty strong effect on cancelling out this sort of negative relationship that we see there. Importantly, our temporary intercrop, which isn't shown here, it had no impact on water and no impact on yield. Also had no impact on grain protein, which we were kind of expecting it might, but we sort of had low nitrogen fixation there. So while we want to talk about carbon, we want to talk soil health benefits. Talk about the adoption of this plant diversity or these plant diversity concepts and practices. We need to understand water use efficiency, nutrient acquisition, and over yielding within these systems, and really look at it at a broad systems and economic context, which is where this work is sort of going in its next stage. What I want to jump back to is nutrient dynamics over fallow periods. So this is from the Facey Group paper, where we have a cover crop grown. You can see we've got bulk soil carbon, bulk soil nitrogen. Our POC-C is permanganate oxidizable carbon, so it's another measure of that labile carbon, similar to what I put up before. So you can see small summer cover crop biomass. We don't get a response in our labile carbon to that, but we do get a response to our cash crop peak biomass. So no treatment differences, but again, that temporal fluctuation. So it's that higher biomass in the cash crop where we're seeing the response in the early cycling soil or soil carbon. And so again, with that very little additional summer cover crop biomass is not resulting in that building of carbon. If we compare it to, and this really builds on what Cass presented before and was talking about with soil fertility, again, so it's back to our water soluble carbon here. We get a temporal response with a lot of variability, which is pretty typical for the water soluble carbon measurements. But this one down here is a new measurement. This is our soil protein, and it's an indicator of bioavailable nitrogen. So it's more of an organic pool of nitrogen that microbes like. And you can see here, in response to this is a winter spring cover crop. So this is our summer fallow period here. We have our soil nitrogen falls off a cliff. And this is a pattern that we see when we go from our partial lay phase into our cash crop, where we have a build-up in organic nitrogen, which is then converted to mineral nitrogen, and then our system, while we'll see an increase in soil carbon under the pasture phase, we then go back to the carbon level that we saw in the cropping phase. And it's this cycling of nitrogen between the organic and inorganic pools. So you'll build up organic carbon, you'll then mine that when the system starts to become limited in organic nitrogen for those microbes to live. So it comes back to that soil stoichiometry. And then you have this where you go back to your baseline carbon levels. And so this is where when Cass was talking about maintaining that baseline soil fertility, that's where that concept fits into building carbon within our systems. Cass talked about soil constraints, so I won't talk about this too much. I'll wrap up quickly. This is a photo from Riv Plains where we have a sodic sublayer and we have really restrictive plant growth. Our soil pit doesn't show the roots, but our canola grows nicely through this acidic neutral layer, hits this dispersive layer, and then grows at right angles. So take time to identify soil constraints that are limiting your yield, because that'll help improve your carbon production. To briefly talk about opportunities, where in cropping systems, we're kind of limited by low carbon levels and low capacity to add that additional biomass. So we're not quite there yet in being able to participate in the ERF and stuff like that. You see sort of novel applications of biostimulants and stuff like that are sort of starting to be thrown around. There's a bit more work to do with those. So while you might see or struggle to see yourself fitting into the ERF, there's other benefits to building carbon and maintaining soil health that are really important. So addressing your soil constraints, improving nutrient cycling, reducing erosion, improving soil structure, they all feed into that carbon story, but they also feed into your yield story. And doing things sustainably then, depending on how things move forward into the future, you have access to carbon markets, but it's also really important for maintaining your social license and leveraging supply chains as well. This is something that is developing rapidly and it sort of fluctuates with interest. Coles came out, so the grazing industry, Coles have come out and said that people aren't interested in sustainability or paying that extra for sustainability. So it sort of ebbs and flows with a bit of flavour of the month. But if the EU is anything to go by, this is going to become more important by showing your sustainability credentials and managing for soil health, managing for carbon, and then managing for yield as a part of that is really important to maintaining market access. So in the Northern Hemisphere, diverse cropping systems, they're really effective at building carbon. A lot of evidence for these, but they don't translate as well to our southern systems. Summer cover crops are probably an opportunistic practice where you have good summer rainfall, but the intercropping methods, we sort of need to dig a little bit deeper into this. Any of you that are familiar with Hayden Thompson, Thompson Agronomy, lives at Tamora. He's actually doing his master's, looking to convert to a PhD on temporary intercropping. Has some really interesting results. If you are interested in the temporary intercropping, I would recommend reaching out to him. And then also for that synchronous intercropping, that high level of biomass production is of interest. Importantly, you need to remember that building carbon is a decadal process, especially when we're sort of dealing with marginal gains in biomass. So it's going to be slow. But if industry can come on board and develop practices for soil health and demonstrating those sustainability credentials, that's going to be really important for adoption of these practices, but also maintaining market access into the future. That's it for me. So I'll hand back to you, Rob, Thanks.
Excellent. Thank you very much, Abe. That was really good. Really good. On your one of your slides, and I'm trying to relate back to which slide it was. Jeff Minchin at LLS locally here at Temora actually put in a comment that the time period for Central Western Riverina, except for 2024, would be seen as a wetter than average, some very wet years between 2020 and 2023. Now, I'm assuming that actually related to about the second or third last slide there, which I'm trying to drag out of my memory banks, but having a bit of trouble with a few things going on. Yeah, that one I think was to do with fallow periods, or maybe, yeah.
Oh,
yeah. If you wanted to make any comment on there or add anything to that, Abe.
Yeah, so I'll actually go back to the biomass part. Basically, looking at the rainfall and putting it into deciles, we've been, or percentiles, for summer fallow, in crop, and then grain-fill rainfall, we've been probably in the top 75% for every year of these trials. They've been wet. I haven't looked at last year yet, because it came in a little bit tight, and we've got some early evidence to show that those summer cover crops have potentially caused a terminal drought, that need to look at that a little bit deeper. But yeah, that is exactly right. Every year of these trials has been pretty wet. So we're dealing with pretty abnormal conditions for when you want to look at something like water use dynamics from building plant diversity. Yeah.
Excellent. No, thanks for that, Abe. That actually helps clear that up a little more. And he's actually come back and added that more about context for the results, some waterlogging impacts perhaps, but also maximum biomass production for the region in that time period.
Yeah, I laugh because the end trials, or the end plots at Central West get waterlogged, and so we have had to deal with really high biomass at one end and then the waterlogging influence at the other end. So yes, that's definitely the case.
Excellent. Unless Cass wanted to dive in, had anything to add from that previous question about balancing farm goals. Cass, do you have anything to add to that? Having time to think about it?
Look, I think the work that Abe showed kind of links that together as well in terms of opportunities to potentially tweak the systems a bit for improved soil carbon inputs. I'd really encourage farmers to have a bit of a look at your systems and seeing how there might be opportunities just to make those tweaks, knowing that we're already kind of 90% of the way there. So as I mentioned previously, and how Abe's reinforced, is that legumes are king in terms of their ability to improve soil organic matter status. So any opportunities there are to bring in legumes into the system, if you don't already, or creatively incorporate them. I know there are farmers in the FarmLink region who are intercropping vetch with wheat in particular, and having quite a lot of success. So it just keep a bit of an open mind, and if there's things that you'd like to have a bit of a play with, then yeah, knock your socks off and see if those little tweaks might maintain profitability while also increasing the diversity of your systems.
Excellent. Thanks very much, Cass. That actually brings us pretty close to the hour that we're aiming at. So I'll actually take the opportunity to wrap up and thank very much Cass and Abe for your input for this. It's been really informative, and sorry. Yes, we do have Felicity.
Yeah, sorry, Rob. There was a question about biochar from Aravind. I don't know if Cass wants to just make a comment about biochar and how that sort of fits into the soil carbon story, just quickly. Sorry. Thanks, Rob.
Sure. I did try and post, but it wouldn't let. I broke the system somehow. But just to say, good to see you, Aravind. And certainly biochar is a superstar, particularly on our lighter soils. It has less impact on our heavy clays because so much of its value comes from that really high exchange capacity and water holding capacity that it brings to systems. The challenge in all our systems is availability and economics of biochar application, knowing the rates needed to have big impact. So when there is a viable, economically attractive biochar industry that we can source from for these regions, then, you know, I think there'll be a lot of interest continuing in that space.
Excellent. Excellent. Felicity, no further addition to that?
No, thank you, Rob. Yeah, I just want to take the opportunity to thank both our presenters for fantastic work. They've been working with us over the last couple of months to present a couple of these webinars, so we really appreciate their expertise and input. And yeah, thank you to you, Rob, and your FarmLink team for presenting this webinar today on behalf of the Soil CRC and New South Wales Government as part of the Primary Industries Productivity and Abatement Program. And I did pop some links in the chat for those who would like some further information about some of the research that was mentioned today, and also links to the previous recordings of the webinars that were held at the end of 2024 last year. I'd encourage you to go back and have a look at those around looking at soil data to determine your soil carbon source capacity, and interpreting that data as well. So yeah, please have a look at those recordings, and we'll be producing some fact sheets to support these webinars, so you'll be able to follow up on any of the links and further information. So keep an eye out for those fact sheets. We'll send links to everybody who's registered for these webinars when those fact sheets are published. So thanks again, Rob.
No worries at all. Thanks very much for that, Felicity. You've actually saved me one little piece. The only other plug that I have is that FarmLink will be actually doing a lot more work in the carbon space, delving deeper into, especially with things surrounding market access, social license and supply chain, and how that is affected. Those details will be linked onto the FarmLink website in due course. So keep your eye out if you're in our region. We'll be running workshops in that regard as well. All right, thank you very much for your attendance.